fan anemometer. This project will measure 4 meters how it will allow mounting devices to act, fan that will freely move the shaft in proportion to the airflow, a way to measure rotation speed, and a calibration method. I will be looking at the device First, I was trying to use the but everyone else the function is going to short and the function is moved by local function. After some testing, I decided to make my own fun stages of the design. This stage is pretty easy to duplicate and rotates surprisingly well even with very slow airflow. The diameter of house is 120 cm and the toy is 170 cm, so I need to after mounting the new fan on the original shaft, I can start to flip almost with the full device. There are multiple ways to measure rotation speed, but I will be using wide settings, a reflective optical sensor which runs both and stability. The system sensor contains infrared sensor and photographs transistor. As you can see, when it is aimed at the white stripe, the optical sensor is reflected back to the receiver, transmitting the infrared fixed black area. I use this rifle signal to add one full rotation. Data is processed by Arduino Uno. You can find links to the system below. After initial test, I decided to use one right strike because its rotation speed reached the data, and it was bigger than one rotation signal. Go back on rotation for each circle and then I recalculate the ground circle. For sure there is a way to calculate the emission value in ground circle right now, just by safe and fast. In my case, I use it from sharp measures and emission value to calculate the anemometer using professional evaluators like and hardware. As of this special device, which I can use temperature, airflow, and it will do a device The goal of this video is only to show general principle underlying mechanical fan anemometers. Keep in mind that the device that I have built, despite the fact that it's pretty precise, it's not very practical because it is extremely loud, causes huge turbulence inside duct, is prone to mechanical malfunction and dust gathering that will lower efficiency of optical sensor. If you liked this video, please hit like button and subscribe to my channel. In future, I have plans to build working models of other measuring methods including pressure and ultrasonic sensors. Welcome to the first episode of the series in which I create makeshift models of different HVAC airflow devices with cheapest possible components. In this episode I'm building mechanical fan anemometer. This project requires four main elements: a housing that will allow mounting device in the duct, a fan that will freely turn on shaft with speed proportional to the airflow, a way to measure rotation speed, and a calibration method. I will be testing my device in circular air duct, so as a housing I will use this short section of Spiro duct. It's made from thick 0.5 mm galvanized steel sheet. At first I was trying to use computer fan with bruceless motor, but in every one I have tested the magnets were too strong and the fan was not moved by low air velocity. After some searching I decided to make my own fan basing on the design of this toy. This shape is pretty easy to duplicate and rotates surprisingly well even with very slow airflow. The diameter of housing is 125 mm and the toy is 175 mm, so I need to disassemble it and scale it down to required size. After mounting new fan on the original shaft, I get perfect fit almost on the full cross-section of the pipe. There are multiple ways to measure rotation speed, but I will be using CNY70, a reflective optical sensor with transistor output and an encoder disk. This little sensor contains infrared emitter and phototransistor. As you can see, when it is aimed at the white stripe, much stronger signal is reflected back to receiver than if the infrared beam hits black area. I use this rising signal to add one full rotation. Data is processed by Arduino Uno. You can find link to the C# code in the video description. After initial test, I decided to leave only one white stripe, because at rotation speed reached inside duct, measuring precision bigger than one rotation is redundant. In the code I count rotation for 6 seconds and then I recount them to rounds per minute. For sure there is a way to calculate coefficient value from rounds per minute to airflow, just by shape of the fan. In my case I will go for shortcut and determine this value for my makeshift anemometer using professional industry-grade device Lindab Ultralink. This ultrasonic measure device can precisely measure temperature and airflow in range from 0.5 to 15 meters per second without any pressure drop, noise or mechanical elements. If you want to know more about it, I will link to technical manual in video description. Now that both devices are mounted in line and connected to HVAC fan, I just need to gather data with different airflow speeds and set the conversion rate from RPM to airflow on my makeshift device. After averaging results from multiple readings, I get the final value. As expected, after adding it to code, readings on both devices are showing identical airflow in meters per second in full range of speeds possible on test equipment. The goal of this video is only to show general principle underlying mechanical fan anemometers. Keep in mind that the device that I have built, despite the fact that it's pretty precise, it's not very practical because it is extremely loud, causes huge turbulence inside duct, is prone to mechanical malfunction and dust gathering that will lower efficiency of optical sensor. If you liked this video, please hit like button and subscribe to my channel. In future, I have plans to build working models of other measuring methods including pressure and ultrasonic sensors.